All right, here we go with your test review for Chapter 4. If you are just jumping into the video, do take a minute to take a look at the instructions or the comments for the announcement that has this attached to it for timestamps for questions that you're specifically looking for, so you don't have to get dig and hunt and dig and hunt. So we're going to go ahead and start with question number 1. Seems like a good enough place to start. This is saying find the inverse of the relation. Whenever we're taking an inverse, we're switching x and y components. So we're going to take our x and y components of each of these points and switch them. So we have 5, 0 becomes 0, 5. Make sure you put parentheses around it. Negative 4, 2 becomes 2, negative 4. We just grab that entire number and switch it. We don't need to worry about the negatives or positives or anything like that. Wherever that number is, it's going to switch from the x to the y or from the y to the x. Negative 1, comma 3, and 6, comma 2. And there's the inverse of our relation. Okay, so that's it for number 1. Moving on to number 2. Determine whether the graph shown below is 1 to 1. Answer yes or no. All right, easiest way to tell whether a graph is 1 to 1 is to use the horizontal line test. So we make a horizontal line, and we ask ourselves, does that horizontal line ever hit the graph in more than one spot? If it ever does, then the graph is not 1 to 1. So this hits in more than one spot all over the place. So like right here and right here, it's hitting the graph in more than one spot. So that is not 1 to 1. This sucker is not. No. Not 1 to 1. Okay, cool. Moving on to number 3. Find a formula for the inverse of the function. If the function is 1 to 1, if the function is 1 to 1, find a formula for the inverse of it. If not, state this, all right? This function is 1 to 1, so I'll show you how to find the formula of a 1 to 1 function. So first we take f of x, and we switch that sucker, we make him a y. Y equals x cubed plus 6. Whenever we find the inverse, we switch x and y. So we're going to take every y and replace it with an x, and we're going to take every x and replace it with a y. Y plus 3 equals, or y to the third power equals 6. So now we want to get y by itself. We need to get y by itself in order to find the inverse of the function. So we're going to subtract 6 from both sides. So x minus 6 equals y cubed. And then we're going to take the cube root of both sides to undo our cube. To undo this y cube right here, we're going to do a cube root on both sides. So we have the cubed root of x minus 6 equals y. And then we can take that y and then again replace it with f inverse of x. So we have the inverse of our function f equals cube root of x minus 6. And then we're done. There is the inverse of the 1 to 1 function x cubed plus 6. Okay, moving on to number 4. Number 4, f of x equals 2x minus 4. Again, this is 1 to 1. This is a 1 to 1 function. So we have f inverse, or excuse me, we're going to take this f of x and make it a y. And that's going to be equal to 2x minus 4. We're going to swap x and y and get that x equals 2y minus 4. And then we want to solve to get y by itself. So we're going to add 4 to both sides to get x plus 4 equals 2y. And then we want to get y by itself, so we're going to divide both sides by 2. So we're going to get x plus 4 over 2 equals y. And then that thing is equal to our inverse, f inverse of x. Or f inverse of x. Should be able to see the negative 1 up there. So f inverse of x. So there is our function. Okay? So that is our formula for the inverse of that function. On to number 5. On to number 5. Okay? This function is a little bit more difficult to tell whether or not it is 1 to 1 or not. So let's go over to our calculator and let's graph it. Let's go over to our calculator and graph it. Okay, so get out your calculator. And to graph this guy, we're going to turn the calculator on. Turn on, there we go. And we're going to go to y equals, and we're going to plug in exactly what this function is. All right, so f of x is our y, and then we're going to type in x divided by the quantity x minus 8. So we're going to start with x, let's put the numerator in parentheses, x divided by the quantity 8 minus x. And then we're going to take a look at this thing and see if, oops, sorry, that got a little shaky there. We're going to take a look at this guy and see if it is one-to-one. So hit the graph button, and we get this picture here that we can see. And let's zoom out just a little bit. Zoom out just a little bit. Yep. And we can tell that by looking at this, it's the horizontal line's never going to actually hit this guy more than once. So because of how our picture looks, and it looks like it's never going to actually have a horizontal line that hits it once, we're going to say this guy's one-to-one. So let's try and find an inverse for it. Okay, same procedure as before. Take f of x, make it y. That equals x over 8 minus x. We're going to switch all of our x's and y's to get x equals y over 8 minus y. Now this is kind of gross because we have two y's now. We have two separate y's. Our goal is still to get all the y's on one side, all the not y terms on the other, to get y by itself. So we're going to go ahead and multiply both sides by our denominator, which is 8 minus y. So that's going to make the denominator go away on the right side, and we're left with 8 minus y times x equals y. So we're going to go ahead and distribute our x to both of these terms and get 8x minus xy equals y. So now let's get all of our y terms on one side of the equation. So we're going to add xy to both sides. 8x equals y plus xy. So from here, these two terms both have a y in common. So we're going to say that 8x is equal to y times 1 plus x when we factor out that y that they have in common. Then we're going to take, we want to get y by itself, so we're going to divide by the thing that we're multiplying it by. So we're going to divide by that guy, and we then have 8x over 1 plus x equals y. And this right here is our inverse. Feel free to set it equal to f inverse of x. Okay? So there is how you get y by itself for that, and that's the inverse of that function. Okay? Cool. Moving on to number 6. Number 6, f of x equals x squared minus 4x plus 4. This function is not one-to-one. This function is not one-to-one. Okay? So let's find the inverse for it. So we're going to take this guy, and we're going to say, all right, y equals x squared minus 4x plus 4. X equals y squared minus 4y plus 4. All right. So then we're going to factor this side of our equation to try and get y by itself. X equals y y minus 2 and y minus 2, or y minus 2 squared. X equals parentheses y minus 2. Whenever we multiply something by itself, we get that thing squared. So to unsquare this thing, we take the square root of x. But when we take the square root of both sides, we have to take positive or negative the square root of x equals y minus 2. Then we add 2 to both sides, and then we get 2 plus or minus the square root of x equals y. And then because of this plus or minus here, our inverse of x, f inverse of x, is not a function. Not a function. Sad face. Okay, so we find the inverse, and then we stated that it is not a function. Okay, on to number 8. Remember, because you're supposed to skip number 7, so don't do it. Number 8, for the one-to-one function, f of x equals x cubed minus 2. Find the inverse of find the inverse, which is going to be called f inverse. Again, take f of x, swap it out for y, and then rewrite the rest of your equation, x cubed minus 2. Then we're going to swap x and y, get x equals y cubed minus 2. Then we're going to add 2 to both sides. We're going to get x plus 2 equals y cubed. We're going to take the cube root of both sides and get that the cube root of x plus 2 is y, or which is just our inverse, f inverse of x. Okay. So that is our inverse. This is our inverse of our function. So then on to number 8, part B. For the one-to-one function, find the domain and range of our function f. Okay, essentially for our domain, are there any numbers that we cannot plug in and then multiply it by itself 3 times? Any real numbers that we can't do that for? There aren't any. So our domain is all real numbers. And then our range, if we take a look at the graph, our graph, it's going to look something like this. Let's turn our calculator back on. Wake up, calculator. Thank you. If we take a look at our graph, it's going to be x caret 3 plus, scratch that, go away you, and then x caret 3 minus 2. If we take a look at our graph, we see it shoot down off the graph here and then shoot way up off the graph up here. So there's no real reason to assume that it's ever going to turn around because we don't see it coming back in any direction. Let's go ahead and zoom 6 this guy. Zoom 6. So there's no real reason to assume it's going to turn around because it doesn't. So it's just going to keep going down forever and up forever. So our range is all real numbers. Our range is all the y's that it's going to take, which is all of them. All real numbers. Okay? So there's the range of our function, the domain and range of our function f. On to part C. On to part C. All right, so there's our inverse. Now we want to find the domain and range of our inverse function. Well, if we take a look at the domain and range of our original function, if we just flip them, if we flip the domain and range, we'll get the domain and range of our inverse. So, since our range was all real numbers for our original function, the domain for our inverse function is going to be the same thing, all real numbers. And since our domain was all real numbers for our original function, the range for our inverse function is going to be the same thing it was for the original. Okay, so nothing too complicated here. Just take the range of your original and the domain of your original and flip them for your domain and range of your inverse. Okay. On to number 8, part D. Now we want to graph f and f inverse on the same axes. All right. So if we remember our graph, we got something that looked a little bit like this for our function, for our f function, and then our f inverse function is going to do something like this, give or take a little bit. Okay, you could graph them on your calculator, get some more specific points, and do all that sort of stuff. But that's approximately what it's going to look like. We're just going to leave it at that. Okay, moving on, skipping 9 and 10 to number 11. Find the following: logarithm base 4 of 3 to the 4th. Says to not use any calculating device. Do it mentally. So hopefully you would be able to do this. So if we take logarithm base 4 of the cube root of 4, it's handy to remember that the cube root is the same thing as the 1/4 power. So we can rewrite this as log base 4 of 4 to the 1/3 power. So this is asking us 4 to what power is 4 to the 1/3 power? Well, that's the same thing as saying 4 to the 1/3 power is equal to 4 to the 1/3 power. Okay, so our answer to this is 1/3. Okay, another way to think of this is if you have logarithm with a base that's the same as its argument, the result is going to be whatever's in the exponent. Okay, they kind of cancel each other out as long as they're the same base and the thing raised to the exponent. As long as they are identical, they cancel each other out. Let's move on to number 12. Number 12, ln e. Same idea. If you have ln of e, it's the same thing as logarithm base e of e. And since we can't see an exponent, we assume our exponent to be 1. So since the base here and our thing raised to an exponent are the same number, they reduce out and we're left with the exponent as our answer. So that simplifies to be 1. Another way you could do that would be just typing ln of e into your calculator and you'd be in good shape. Okay, on to number 13. Convert into an exponential equation. Convert to an exponential equation. So we have log of x equals 12. So one thing is that's important to remember with this is we have logarithm of x is the same thing as saying log base 10 of x equals 12. All right, whenever we're rewriting an exponent, whenever we are rewriting a logarithm as an exponential, we want to take whatever the base is. So in this case, it's 10, and that thing becomes 10 to the 12th power equals x. Okay, 10 to the 12th power equals x. So 10 here to the 12th power equals x. Okay, and this is just asking us to rewrite it as an exponential equation. We don't need to solve it. Okay, only solve it for the variable if I ask you to do so. All right, so this we just needed to rewrite it. Next, we wanted to convert an exponential statement to a logarithmic statement. So we have 5 to the x power equals 60, which then converts to logarithm base 5 of 60 equals x. Okay, and again, this 5 matches this 5 here. This x goes on the other side of the equal sign, and the other side of the equal sign goes into the argument of the logarithm. Same pattern every single time. Okay, whether you're going from an exponential to a logarithm or a logarithm to an exponential, it's the same placement of everything. Okay, but this would be your answer. Rewriting it as a logarithmic equation. Again, didn't ask us to solve, just wanted us to rewrite. So let's just rewrite. So next, we want to evaluate some of these numbers. So 15 is where we start to evaluate some of the numbers. So ln of 0.8. Not a whole lot we can do with that as far as mental math goes. So let's take a look at the old calculating machine. All right. So wake it back up. Quit back to your home screen, to your main menu here. And then we're just going to type in natural log of 8. Remember, ln key is over here. Natural log of 0.8. Then close the parentheses, and we get a number. 0.22, negative 0.2231, blah, 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 blah. Okay, so you would just say, try to figure out how many decimal places I'm asking you to round to, and then round to that number of decimal places. In this case, let's round to the nearest 3 decimal places. So we're going to get negative 0.223. All right, just like that. Easy peasy. Type it into your calculating machine. Next, we're going to look at log base 10 of 1/2. This is another one we can hammer into the calculator. So let's do that. Log base 10 of 1/2. The two logarithms that your calculator can do are right here, ln, which is logarithm base 3, or logarithm base e, excuse me, and then this guy right here, which is logarithm base 10. So if we don't see a base, we're looking for the base 10 version of our logarithm. So log base 10 of 1 over 2, log base 10 of 1/2 gives us a decimal. And let's again round to 3 decimal places. So it's going to be negative 0.301. Right, negative 0.301, and that is our answer. We just hammer that sucker into the calculator and get an answer out. Okay, so this is a logarithm that we can't use our calculator for. All right, but we need to use the change of base formula. All right, change of base formula is going to be log base b of c equals a. In order to change our base, it's going to be log of something else, so log of some other base. I'm just going to use the common log, or the log base 10, so we can enter that into our calculator. Log base 10 of our original argument over log base 10 of our original base, and that's going to be some number a. So in this case, we have log base 2 of 10, so this is going to become, we can rewrite this as log base 10 of 10 over log base 10 of 2. And that'll give us some number. Let's go over to the calculator and hammer it in. Then we have log of 10, make sure you close your parentheses, divided by log of 2. And we hit the old enter key, and we find out that we get 0.33219, blah, 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 blah. So let's round again to 3 decimal places and go to 3.322 is our answer for log base 2 of 10, which again, hopefully makes sense because this is saying 2 to what power is going to be 10? 2 to what power is going to be 10? Well, 2 to the 0th power is going to be 1. 2 to the 1st power is going to be 2. 2 squared is going to be 4. 2 cubed is going to be 8. And then 2 to the 4th is going to be 16. So 10 is right in between 8 and 16. So our answer should be between 3 and 4. Okay, and it is. It's 3.33322. Okay, so some ways that you can, some things you can look for, so that way you're not just completely relying on your calculating machine. Get a sense for these things. All right, on to number 18. Express as a single logarithm. Express as a single logarithm. So, whenever we're smashing logarithms together, again, remember I want you to start by writing just the log base whatever. In this case, it's log base c, and then a big old fraction. Log base c of our big old fraction, and then any of these terms that are positive are going to go. The argument is going to go on top. Any of the terms that are negative, the argument is going to go on the bottom. So this guy right here is positive, so we're going to take the square root of x and put it on top. Then we have this guy. This is positive, so we're going to multiply by y. That's also going on top. Now, this guy right here, this last guy has a 2 in front, so we need to move that 2 into the exponent before we do any kind of stuff. So it's going to be, this guy becomes log base c of z squared, but this whole thing is negative. This guy's negative, so it wants to go, the z squared wants to go on the bottom. Z squared wants to go on the bottom. Feel free to throw a big old parentheses around it. And there is our single logarithm. Square root of x times y over z squared. All right, so that's number 18. Number 19 is the opposite. We are going to take a large exponential statement and express it in terms of sums and differences of logarithms. So we're going to take one logarithm and expand it. Okay? So let's do that. Let's do that. So we're going to take logarithm of a logarithm base 10. Remember that we can write the cube root as to the 1/3 power. So we're going to go x squared over y. That whole thing to the 1/3 power. Now we have a logarithm, so this can come out front. So we're going to have 1/3 log of x squared over y. So now we have a 1/3 that's just going to kind of be along for the ride, times, now we're going to split this argument up because there's a division sign. We're going to subtract the 2, so log of x squared minus log of y. And then we want this exponent to come out, so it's going to come out front of its individual logarithm. So 1/3 times 2 logarithm x minus logarithm y. And then we're done, because we have one thing in the argument for each of our logarithms. On we go to number 20. All right. I overlooked this when I was putting down the instructions for your assignment. Skip it. You won't have one on your test. You won't have one on your test. Skip it. Okay? Good talk. 21. Simplify. We want to get this to be somewhat a little bit easier to work with. All right? Well, again, we have ln of e to the x plus 6 power. But again, this is logarithm base e of e to some exponent. So ln and e cancel each other out, and we're just left with x plus 6. We're just left with x plus 6. Whenever you have a logarithm of a base of that thing, of whatever that base is to some exponent, they cancel each other out. So go ahead and do that. Okay, on to number 22. 22 is log base 5 of 125 equals x. Now this is asking us to solve this equation. All right. So the way that we're going to solve this equation is we can evaluate this in our calculator. we can do stuff like that. I think evaluating the calculator is probably going to be the most straightforward way to do this, but we can't do logarithm base 5 in the calculator, so we're going to change a base formula. So it's log base 10 of 125 over logarithm of 5 equals x, and so we're going to find some number for these. Let's go ahead and get our calculator back out and wake up. So then logarithm of 125 log 125 divided by log of 5. Now, if you recognize that 125 is 5 to the third power, then you could have just written the number 3 in place of log base 5 of 125. Or, if you use a change of base formula, you find that x is equal to 3. So, 3 equals x. Okay, that is our solution. All right, we'll try to find the value of x that makes after true statement, and 3 is indeed it. Now if we take a look at this one, whenever we have a logarithmic statement, a logarithmic equation, we want to get a logarithm on one side, everything that's not a logarithm on the other side. That's our goal. Okay, and again, refer to those several step processes that we wrote down. Should have about 3 of them for different scenarios. So this is one of those scenarios. We want to get one log on one side. Since these guys are being added together, we're going to multiply the arguments together. So we're going to start with log base 5. We're going to multiply those two arguments together. So we're going to get x minus 2 times 2x minus 9. Then that is equal to 2. So when we distribute in here, we're going to get logarithm of 5 times x times 2x gives us 2x squared. X times negative 9 gives us negative 9x. Negative 2 times 2x is negative 4x. Negative 2 times negative 9 is positive 18. So that's our distribution, equals 2. And then let's combine like terms and do all that sort of good stuff. So we have logarithm of 5 times 2x squared. Negative 9x minus 4 more x's is negative 13x's plus 18 equals 2. So now, once we have one logarithm of some stuff equals a number, we want to rewrite this as an exponent. And when we do that, we get 5 squared equals 2x squared minus 13x plus 18. We see this square right here. That tells us that we're going to want to get 0 on this side. But 5 squared is equal to 25. So to get a 0 over here, we're going to subtract 25 from both sides of our equation. 0 equals 2x squared minus 13x minus 7. Okay? So now, we need two numbers that when we multiply them together, we're going to get to be negative 14, because we have this 2 up front here. So we need to do 2 times the first number times the last number. It gives us negative 14. That when we add those two things that multiply to be negative 14, we're going to get to negative 13. Those two numbers are negative 14 and positive 1. So 2x squared plus 1 minus 14x minus 7. So now we want to ask ourselves, what do these first two terms have in common? The first two terms have that should be an x, 1x. First two terms have an x in common. So that equals 0, 0 equals x times 2x plus 1. And then we have negative 14x minus 7. Those two things have a negative 7 in common. Then we're left with 2x plus 1. And then we ask ourselves, what does this first term have in common with the second term? And we get that this first term has 2x plus 1 along with that second term, and then we're left with x minus 7. Okay. Now we multiply both of these things. Both of these things multiply to be 0, so one of them has to be 0. At least one of them has to be 0. We don't know which one, so we set both of them equal to 0. 2x plus 1 equals 0. X minus 7 equals 0. So then we're going to solve both of these for x. Subtracting 1 and then dividing by 2 gives us x equals negative 1/2. And then adding 7 to both sides, we get that x equals positive 7. Now we want to check these to see if either of them don't work. Essentially, we're looking to see if when we plug them in, do we get any logarithms of negative numbers. So if we take negative 1/2, we plug it in up top, if we take and we plug it into our original equation, negative 1/2 minus 2 is going to give us a negative number, which is going to break everything. So x equals 1/2 doesn't actually work as a solution for us. It's no good. So then let's check 7. If we plug 7 in, 7 minus 2 is going to be positive, and then 2 times 7, which is 14, minus 9 is still going to be positive. So 7 is going to be a valid solution. So x minus 7 is the solution that we want. Okay. On to the next problem, on to 24. All right, now we want to solve this guy. This guy is a exponential equation. So we want to get it to where we have one exponent equals the same exponent. One exponent equals the same exponent, or if we can't do that, since we have two things with an exponent, we want to take a logarithm of both sides. Let's do that. Logarithm of both sides. So log of 3 to the 5 plus 4x equals log of 9 to the x. Once we have this, we can take both of our exponents and move them out front. So then we get 5 plus 4x times log of 3 equals x times log of 9. Okay. So now we have a little bit of distribution that we need to do. So we're going to do 5 log 3, 5 log base 10 of 3 plus 4x log base 10 of 3 equals x times logarithm of 9. Once we get to here, we want to move all of our variable terms over to one side. So I'm going to take this 4x log 3 and then subtract it from both sides to get to the other side. So we get 5 log of 3 equals x times log of 9 minus 4x log of 3. Okay. Once we get all of our terms that have an x on one side, then we factor out the x from all those terms. So we have 5 log of 3 equals x times log of 9 minus 4 log of 3, because we factored out the x from both of these terms. We factored out that x, and it is now right here. So then we want to get x by itself, so we're going to divide both sides by this entire thing. We're going to divide both sides by that whole thing, and we're left with 5 log of 3 over log of 9 minus 4 log of 3 equals x. So then we head back to our handy dandy calculating machine, and we hammer that sucker in. Okay, this is where we got to be real careful with our parentheses. So let's make sure we put the entire top of our equation in parentheses. Parentheses 5 log of 3. So we want to close our parentheses for our log, and then we're done with the top of our fraction. So we close off the top of the fraction. Divided by, start at the bottom of the fraction with the parentheses. Then we hit log of 9. That logarithm's done, minus 4 log of 3, and then that logarithm's done, and then the bottom of our fraction's done. So we put another parentheses to close off the bottom. Hit the enter key, and we get negative 2.5 equals x. Negative 2.5 equals x. And that is our solution. So again, we want to check and make sure. I'll leave this as an exercise for you, but check and make sure that that thing works by plugging it back in up top. Okay, negative 2.5 equals x. Make sure that you plug that back in to make sure that it is a true statement. All right, next we have e to the 2x equals 10.4. Since we have only one logarithm this time, only one exponent with a variable, only one of the terms has a variable exponent, we can just get the term that has a variable exponent on one side by itself, and then all the numbers on the other side. we have that right now, so we can then rewrite this as a logarithmic statement. So we have log base e of 10.4 equals 2x. If you already recognize that log base e is ln and want to just rewrite it as that, go for it. You're absolutely welcome to do so. So ln of 10.4 equals 2x. We want to get x by itself, so we're going to divide both sides by 2. We're going to get ln of 10.4 over 2 equals x. And then we head over to our handy-dandy calculating machine, where we get natural log of 10.4 over 2. Whoopsie, forgot to close my logarithm. That was embarrassing. 10.4 over 2 is 1.17. And then let's give 3 decimal places, 1.171. So then 1.171 equals x. And again, plug it back in, make sure it works. So that way you can verify that it does indeed work. Okay. Next, put down your markers before you try to swipey swipe on smartboards. Put down your markers before you try to swipey swipe on smartboards. That's a thing. Next, problem 26. The population of a country doubled in 30 years. What was the exponential growth rate? This is when we need to use our doubling time equation. So that is natural log of 2 over the rate equals time. Okay. If we know that time is equal to 30 years and we're looking for the rate, we're trying to get r by itself. So natural log of 2 over r equals 30. And then, so we need to multiply both sides by r. Natural log of 2 equals 30r. And then divide both sides by 30, and we get natural log of 2 divided by 30 equals r. So let's find out what that is. Head over to the calculator, and then we hit natural log of 30, close your parentheses. That number divided by, whoopsie, natural log of 2 divided by 30, silly Seja. Natural log of 2 divided by 30. Natural log of 30 divided by natural log of 2 divided by 30. Words is 0.023. So r equals 0.023, which, if we then express that as a percent, is going to be 2.3% is the growth rate. Cool. So remember that doubling time equation. Doubling time. Remember that guy. Next. All right. Another multi-parter. So we're going to suppose that we have invested $5,000 at some interest rate that is compounded continuously, and it grows to $6,954.84 in 6 years. So we know that P is equal to 5,000. And we know that the amount in that account after 6 years is equal to $6,954.84. And we need to find the interest rate. So we need to find R. So it's compounded continuously. So that word lets us know we need to use the P e to the RT formula. A of t equals that. So let's write that equation. A of t equals P times e to the RT. And we know that A of t equals the principal, which is 5,000, times e to the rate, which we don't know, times time, which we don't know. However, we do know this other bit of information, so let's say A of 6. Well, A of 6 is 6954.84, and that equals 5,000 e to the r times 6. Okay, we got that from that second bit of information. So now we want to get r by itself. So we want to get the e term by itself on one side before we can start working with that r. So let's divide both sides by 5,000. So we have 6954.84 over 5,000. That's going to give us some number. I could calculate it out, but I don't really feel like it, so I'll just calculate everything out at the end. If you want to get this this fraction into a number, please feel free to do so. So I have some number equals some exponential statement, so I want to rewrite this as a logarithm. All right, log base e is going to be ln of our argument of the other side of the equal side is 6954.84 over 5,000. And then that's going to equal r times 6. So then we're going to divide this thing by 6, and that's going to give us, we're going to divide both sides by 6, and that's going to give us r. So let's go ahead and figure out what that number is. Head over to your handy dandy calculator. Natural log of 6954.84 divided by 5000. Close your parentheses for your logarithm, then divide by the number 6, and that's going to give us our growth rate, which is 0.0549, or let's just do 0.055. So r 0.055. Okay, so we're going to use this for the rest of our equation, but if we wanted to have that as a percent, is 5.5%. Okay, but we're going to use that number 0.055 for the remainder of the problems for number, what is it, 27. Yes, we did it. All right, so we want to find the exponential growth function. So this is just using that r, find the exponential growth function. So a of t equals p e to the rt, again, because of this word continuously. And then we replace stuff that we know. So a of t equals p, which is 5,000, times e to the r, which is 0.055 times t. There is our exponential growth function. Okay, on to 27 part C. All right, now we want to use that exponential growth function and find the balance after 10 years. So because I am lazy, I'm going to move this circle and I'm going to copy paste this. Copy. Come back, circle. Yeah, there you go. Good stuff. And then I'm going to paste. All right, so there's our exponential growth function. And find the balance after 10 years. When it says find the amount after 10 years, find the balance after 10 years, we plug in 10 for t, wherever we see a t. So our amount after 10 years is going to be 5,000 e to the 0.055 times 10. Once we have that, we're just going to hammer this sucker right here into our calculator, and that's going to give us some number. A of 10. It's going to give us some number. So we head back over to the calculator, and we find that 5000 second e to the 0.055 times 10 is equal to $8,666.26, or because it's 0.265, we're going to round it up to 27 cents. So $8,666, $6.27. Okay, and again, I only went to 2 decimal places because this is money. Money ends with pennies. Okay, so $8,666.27 after 10 years. After 10 years. Okay, so once we have that, we want to find the doubling time. So if this is our equation, we found the rate, which was this, so we need to use that doubling time equation again. So natural log of 2 over r equals t. So find out how long it's going to take for the amount of money to double. So we're going to take natural log of 2 over 0.055. That's going to give us t. So we head over to the handy dandy calculating machine one more time. Natural log of 2 divided by 0.055. Hit the enter button. and we get that after 12.6 years. So 12.6 years. After 12.6 years, we have our number. We have our amount. Okay? Cool? All right. That is our doubling time, 12.6 years. So we're going to solve this equation. All right. Again, we have a number to an exponent. So let's get that thing by itself. We're going to start off with 5 to the 4th root of x equals 15. So we divide both sides by 5. So we're going to get 4th root of x equals 3. Dividing both sides by 5. And then to undo a 4th root, we take both sides of the 4th power. X equals 3 to the 4th power. So 3 to the 4th power is 3, caret, 4, enter. 3 to the 4th power is 81. So x equals 81. And then again, go ahead and hammer that back into your equation, make sure it works, so that way you can verify that you are correct. So, last but certainly not least, there was a problem that none of the problems on your review had another Lie word that wasn't continuously. So I wanted to give you a problem that had that. So, if you have a bank account, bank account in, okay. In 2033, we started in that started in 2033. Yes. Okay, never mind. Whoops. Hang on one second. I'll be right back. Okay, I think I have fixed it. I think I made words make sense now. Okay, so how much money will be in a bank account in the year 2033 if it started in 2018 with $8,000 and gains 4.3% interest compounded monthly? Okay, so let's set up our equation. All right, we have a Lie word that is not continuously, so we need to use the word or the equation a of t equals p times 1 plus r over n to the nt. All right, so this is going to say, all right, a of t equals the amount we started with was $8,000, and 1 plus the rate is 0.043, and our Lie word was monthly, so there are 12 months in a year. So that n goes both in the bottom, the denominator there, and up top here, and then times t. So we're going to evaluate A of how many years pass between 2018 and 2033. Well, that's 15 years. 15 years equals 8,000 times 1 plus 0.043 over 12 to the 12 times 15 power. Okay? So we're going to hammer that sucker into our calculator, and we're going to get a number. Get a number back. All right? So again, careful with your parentheses. Start off with 8,000 times 1 plus the quantity, 0.043, divide that by 12, close your parentheses for your fraction, close your parentheses for the entire parentheses, caret to the 12 times 15 power. Now be really careful. Be really careful with this exponent. If your calculator doesn't just sort of bump things up like this, you'll need to put parentheses around your exponent. Okay? If your calculator just shows you like a little caret key, make sure you put parentheses around your exponent. Okay? If it does bump it up like this, you're good to go. So once you have that, hit the enter key, and this says that we'll have $15,230.33 in 2033. So that's 15,000. Wow. Words. 15,230.33. 15,230.33. Okay? That's how much money we will have in the year 2033. So let's say we have an account that's pretty much the same, but instead of compounding it monthly, we're compounding it continuously. In what year will that account have $20,000? Well, we're going to use our A of t equals P times e to the RT power. And with that, we then are going to replace all of our variables. So we have A of t equals 8,000 times e to the rate, which is 0.043, times some unknown amount of time. All right, so now we're looking for $20,000. So this is the amount that we're going to end up having, so we're going to plug that right in for A of t. So 20,000 equals 8,000 times e to the 0.043 t power. So then our goal is to get this e term by itself. So we're dividing both sides by 8,000, and then we get 20 over 8 equals e to the 0.043 t. And if you want to reduce that to like 10 over 4 or let's see, 5 over 2, you're absolutely welcome to. As a matter of fact, I think I will, because it's easier to write that, 5 over 2. So we rewrite this, now that we got this guy by itself, now that we got that guy by itself, we want to rewrite it as a logarithm. So logarithm base e is ln of 5 over 2 equals 0.043 t. Okay, 0.043 t. We're going to divide both sides by 0.043, and we're going to get divide by 0.043, and we're going to get a number. We're going to get a number, and that is going to be the number of years that will pass before we hit $20,000. So if we hit ln of 5 over 2, oops, one too many parentheses, that's okay. ln of 5 over 2 divided by 0.043, we get this number, 21.31-ish. Okay, so this is going to be t equals 21.31. But remember what the question asks. In what year? If you know what year it started, so in what year, right here, in what year will that happen? Well, 21.31 years are going to pass since we opened the account to get to $20,000. But if we start in 2018, we have to add 21.31 years. So 2018 plus 21.31 is going to be, let's see, 2039.31. So like March-ish, April-ish of 2031 or 2039. So this is the answer that I'd be looking for. This is the answer that I want. Okay? Cool. So that is your entire review. That's the whole thing. Okay? All right. Again, take a look in the comments. I'll have timestamps and everything. And happy snow day, and I will see you tomorrow. Have a good one, guys. Bye.